Thank you. I'm very happy to be here to talk about our evil plans. And so the kind of the slogan for this meeting is this bridging the gap. And then if you ask a mathematician what this gap is, you get maybe something like this. We have on the left, we have sort of math, right? And it ranges from things that are still kind of math, but are maybe a bit informal. You wave your hands and say, well, yeah, but it's still sort of convincing. It still maybe counts as a proof. You can maybe weasel your way out. And then you have sort of the extreme case for mathematicians is people who are what I like to call quasi-formal. So they try to be really keeping the formal things in mind. So the example that I tend to go to is there's a book by Schwabhäuser on Tarskian geometry, and he's really writing first-order logic in his book. And of course, you probably also know some other examples where someone really clearly has some kind of formalism in mind, and they try to write their textbooks, their papers, with this formalism quite explicit in the background. And then there's the gap, this is the dotted line, and then there's this weird thing that these people with their proof assistants are doing, this formal math. But of course now we have seen sort of more collaboration between people who do proof assistants and mathematicians, so there's some communication across the chasm. But of course this picture is too simple. I use something more like this. So it's some kind of large space of weird parameters, and you can make all sorts of choices on how you do things. Like you have different syntaxes, you can choose different foundations, right? There's informal homotopy type theory that you can do. You can choose the level of detail in your proofs, right? A proof that is intended for undergraduates is going to have more detail than some paper that's only meant for experts. And this is sort of the formalism in this large space. And within this large space, I purposely didn't label anything, so I don't have to put meta math in the overly formal area and then get some kind of complaints. So this is very vague, so I cannot get attacked. But you can imagine in this weird large space, there's some area that is formal and some area that is informal. And maybe they overlap, maybe they don't. This may be some interesting topic for discussion. But anyways, we want to kind of increase or get some kind of area of intersection. And one approach is this weird Naproche thing that I've been doing with Peter Kapke. And this is what I did for my PhD project. So this is an example formalization. And this really is the formalization. So this is not some kind of weird pretty printing or something. Well, it is pretty printing from the LaTeX source, but this is really the formalization. And hopefully you can read it like a regular mathematical text. And you can see it's fairly declarative, fairly high level. And what happens here is if we look at one particular proof step, so this is this B is an element of the power set of A. What happens is at that proof step, we kind of create a proof task that is sort of implicit within the structure of the proof. And we take all the stuff that came before, all the lemmas, definitions that we made before as kind of global premises, and then the local stuff. So in this case, for example, we don't have any assumptions in the theorem, but they would also appear here. But we have this definition of B that appears. And there I want to point out that the definition in the original text is higher order, right? We have a set comprehension in which there's a term with a formula inside of it. But of course, in this case, we can kind of flatten it out and break it down to first order, and then we can use a first order automated theorem prover like Vampire to solve this proof task for us. And of course, something like this is very, very easy for Vampire. It takes a fraction of a second to do this. And the whole proof goes like this. All the steps get verified by Vampire, and we're happy. And so this talk might look a bit like a propaganda talk for controlled language, but it really is supposed to be a propaganda talk for automated theorem proving. So this is really my actual goal. Of course, the syntax is kind of flashy, but the real pitch is automated theorem proving. And actually, I also want to kind of get into this de Bruijn factor thing, right? So there's the notion of a de Bruijn factor. How much longer is your formal proof compared to the informal proof? And I would say maybe in this example, depending on, again, the context, this is pretty much de Bruijn factor 1, right? This is kind of, you would maybe find this acceptable as an informal proof. But in actuality, we could get a much shorter Bruijn factor because after the definition of B, this is already trivial for vampire. So this could be like a 1 or 2 statement proof, and we could just leave the rest of vampire. And there are many other cases, of course, where vampire can just prove something just from the theorem statement alone. And I will kind of get to that later. So in this case, the proof is really for the human reader and not for the computer. And just to give a peek behind the curtain, so at the top again, we have some kind of formalization example, and then below you have the actual source that I write to formalize things. So this is, as you hopefully can see, is more or less just regular LaTeX that you would write anyways. So the only kind of quirk here is that I require people to always label the theorem so that I have nice export names when I export things to the automated theorem prover. So this is sort of the only thing that is a bit unusual here. And of course, the fact that you have to conform to the controlled language, which is some kind of formal sublanguage of regular mathematical English. But I will get into this later as well. So for a bit of historical context, so I kind of dug up some old stuff from the 60s. And there already we had this kind of bridging the gap idea. And they were quite ambitious, maybe a bit naive, of course. So the goal here for this, like this was initiated by McCarthy, was to verify textbook proofs as they are written. So this is some kind of semantic de Bruijn factor of 1, ideally, right? So they don't model the syntax of the language, but they try to model like the semantic structure of the proofs. And even earlier, this was some kind of idea. So there's some really early paper by Hao Wang, where there's some kind of formalization of stuff from Principia. And here again is sort of this idea of, yeah, well, we just write the outline and the machine fills in the rest. And this is basically, well, this automated theorem proving idea that I showed earlier in the examples. And sort of in the 60s, this didn't work. But maybe now's the time to actually do this at scale. So to kind of zoom out, to give the sort of a whole history, slightly biased, of course, by my perspective. So we have in the early 60s, we have this emergence of automated theorem proving. And then quite early on, especially in the East, we have these projects that kind of wanted to implement this machine verification of mathematics as it's done already. So we have the MISA project, which still sort of continues on nowadays. And then we have this evidence algorithm, or EA, project initiated by Glushkov, which also had this idea of, well, surely eventually the machine will be able to check everything. And then there's some kind of suspicious gap, which is sort of the AI winter, maybe. And then we have sort of the more modern things. So we have the kind of modern variants of controlled language, for example, the grammatical framework, which developed at Xerox. And then sort of for the historic context for the system that I'm working on, very important is SAD, so the English SAD by Paskiewicz, so in the early 2000s, which was sort of the first system that implemented this idea in practice in a sort of usable way. And then, of course, we had other things. I mean, very prominent here is Sledgehammer, this idea of having automated theorem provers fill in the gaps. So you just have a one-click thing. You say, Sledgehammer, please solve this step for me in this Isabel Hall thing. And then you get, hopefully, a solution from the automated theorem provers. And of course, the Sledgehammer has changed quite a bit since this first prototype from 2007. And now we also have many advances in automated theorem proving. So in the last couple of years, for example, we had many advances in high-order automated theorem proving, which also helped Sledgehammer, of course. And then for the more recent developments, especially on the approach side, so we had this continuation of SAT in Bonn, sort of trying to scale it a bit further. And we got to chapter size, and then we ended up with checking times of multiple hours. And you kind of run into some scaling problems, especially if you have a more complicated theory. So there were students, for example, doing representation theory, and you end up in some weird corner cases. So things are still quite tricky. And I did implement this NAPROCH-ZF system sort of in an attempt to simplify some things and scale it a bit further. And I will jump into this a bit later. And now, of course, we have Malinka, and maybe this will also go in a similar direction. So the prominent thing here is the Godemo challenge, right, which is this idea of taking a textbook and kind of representing it in a faithful way in a formal system. And just to kind of show that SUT already was quite far ahead, maybe. So this is maybe circa 2007, 2008-ish, and we have this proof in SUT. And these are kind of all one-off formalizations. So these are small, self-contained formalizations with sort of ad hoc axiomatic setups. But you do get something that looks quite nice. And this worked with technology of the early 2000s. And of course, automated theorem provers have come quite a way since then. So this was sort of a nice thing that already existed. And then just for fun, I dug up some example from the proof checker thesis that Abrams wrote. And so there's this example sentence. And below is the proof checker representation, so it's kind of Lisp thing. And then in Mizar, you could render it maybe like this. And below that, we have some SUT rendering. So this is some kind of ASCII syntax for this. And then below that is something I can write in approach.def. So this is the LaTeX source code I would write. And then with the suitable rendering definitions, I just make it so that the mul is invisible and the unit renders as an E or something. And then I get pretty much exactly the thing that was written in the original. And of course, there's some kind of asterisk where I need to make some kind of technical definition so that an element means the right thing in context. So there's some kind of mechanism that keeps track of structures and sort of which structure is in scope is an implicit thing. And then an element can be expanded to an element of the structure that I'm talking about. So there's some kind of caveat, but we can basically approximate the thing that was there. And then now to sort of jump into the more detail on this natural theorem proving thing. So this is the distinctions that Paskiewicz makes when talking about SUD. So there's syntactic checking. So this is things like, can I parse the input of the user, right? Is there some kind of typo? Is everything, is the vocabulary defined? And of course, with natural language, you can write sentences that are ambiguous. So in my case, I have a grammar, which is just a context-free grammar. And of course, I can mess up in the design of the grammar and make something ambiguous. And of course, the users, since there's some kind of way of defining new vocabulary, you can define vocabulary in a way that is potentially ambiguous. So this can go wrong and needs to be checked. Then there's the logical checking, which is sort of the main thing that goes on. And this is done with automated theorem provers, as I've shown in the example, right? So we kind of go step by step and show that everything follows from the previous stuff. And then there's this sort of more quirky thing of ontological checking. So in other proof assistants, this would be called type checking, maybe, right? In ROC, in Lean, in ACTA, this would just be type checking. But of course, you could expand this to things like counter model finding, right? If I write some fancy definition of a new class of topological spaces, but the class is empty, then I've probably made a mistake, right? So this kind of idea. Or if I have some kind of axiomatization, but the axioms themselves are already contradictory, I've probably also made a mistake, right? So this is this kind of idea. You're not even wrong. You're so wrong. It's not even math anymore. And this is also part of ontological checking. And then to kind of peek behind the curtains of the syntactic checking. So there's this aspect of mathematical language that it's dynamic, right? I can come up with new notation. I can come up with new terminology. And to model this, there's in my system, there's a process that kind of scans through the entire text and tries to extract all the vocabulary. And this sort of works like this. So there's some kind of, basically it's just a fancy regular expression, and it tries to, by the structure of the definitions, figure out what the things that are being defined are. And then there's some very simple paradigms that kind of guess what the plural might be if you just define a noun and these kinds of things. And you can, for the symbolic notation, you can use pretty much any arbitrary LaTeX patterns as long as there's some kind of symbol between the variable slots. But sort of the system encourages using semantic macros. So this means for any new symbol, you would define a dedicated LaTeX macro, and then you can freely change the notation later by just redefining that macro. So this is the kind of idea here. So the union symbol, for example, would just be \union, which is what you would write. So you can later, if you want to do some square union or something, you can change it to that. And then the parsing, so for that, I'm using a declarative approach, a grammar-based approach. So I have, there's a library, so I'm implementing this in Haskell. There's a nice library called early, which more or less lets me write the grammar, something like this, into the Haskell code, like in a declarative format. And here I've kind of split the grammar, so this is some kind of BNF-like notation. I've split the grammar into the dynamic part. So this is the stuff that a user would write, like new definitions. This can be expanded as you go along the text. And there's sort of like a static skeleton that ties things together. So there's a fixed way of combining these sort of atomic statements, for example, into a more complex sentence. And yeah, this is a declarative thing, and then I get an early parser, and then I get a reasonable parser performance. So this is some worst case cubic thing, but in reality, this like collapses at each sentence pretty much. So this works quite okay. And the big benefit of doing this declaratively is that whenever I want to add a new feature, I just like add a new line to the grammar, and we're off to the races. This is kind of in contrast to SUD, which uses parser combinators, and there you get into trouble with backtracking and ambiguity tracking and this kind of stuff. So this was a nice improvement. And then once we have sort of this first syntax tree after parsing, we kind of do transformations bit by bit to get things closer to formal logic. So there's some very simple examples. So for example, you can chain relation symbols. So something like A is less than B is less than C would get expanded into a conjunction. Then the second example here, and of course you can write like A comma B is less than C, which would get expanded also into a conjunction. Then the second thing is, so you can in set theory you sometimes see this where sets are used as relations, so there's some syntactic sugar for that, and it just gets desugared into, well, the tuple is an element of the set, and then there's various sort of more language focused things, so you can implicitly quantify things, so you can like omit the variable, at least locally, and it like adds the variable back in to make it closer to logic. And there's like very limited sort of almost pragmatic phenomena where, for example, if I have a proof and I make a proof step and I say there exists something, well, on the surface this is just a bare existential statement, and I'm not binding the variable, right? If I just translate this into some intermediate claim, I'm just saying, well, there exists an x, I prove that the x exists, and then I move on to the next step and the x is gone, which is of course not what a human writer and reader would get out of the statement, right? If I'm telling you something exists, I'm telling you for a reason, and I want to use it in the next steps. So this is kind of like the key word in this like proof language is consider, right? So this is kind of like show that it exists and then remember that it exists, and the sort of bare existential gets translated into this explicit consider. And then the other nice thing of using LaTeX is that we more or less get literate formalization for free. So the way this works is I take in the LaTeX source, and I just look for formal environments, so something like begin definition, begin theorem, begin proof, and those are analyzed, and everything else is treated as commentary. So I can freely mix formal content and informal commentary in the same document, which is very, very nice. And I can also just like, by renaming the environment, I can switch, for example, a theorem to be an informal theorem. And the other benefit, of course, is with this controlled language thing that I don't have to restate the theorem, right? This is sometimes something you would see maybe in some other systems where you have the formal statement accompanied by some kind of informal version of the same statement. In this case, the formal statement is already as readable as the informal statement. So there's no issue of like syncing and duplicating and so on. And then the other idea, sort of this is a spoiler for the rest of the talk maybe, is that sort of this literate formalization approach is maybe a nice interface for autoformalization. So you first write a draft, some kind of blueprint in an informal way, and then you like incrementally swap out the informal proofs for the formal proofs, the informal definitions for the formal definitions, and so on, within the same document. And you kind of like work your way through the document. And then very briefly on automated theorem proving, just as an overview. So there are things that are still very hard for computers to sort of prove in a natural way. So I have some examples like proof by analogy, right? So sometimes humans do something, oh yeah, this is the same as that, but it's really not, right? And then, but somehow this is enough for to be convincing, or enough for the reader to like reconstruct the proof if they really needed to. Whereas this might be very hard for a computer to do. We have certain geometric intuition, right? Like in topology, there are sort of informal ways of proving things about topological spaces or about surgery or something, where if you really wanted to spell this out in a formalism, like on the level of first logic, this would be quite complicated. But humans can somehow like justify their way of proving things in this way. So this is an informal way of proving things, but it's still a way of proving things, and we cannot model it nicely with a computer at the moment. And then there's all sorts of other ways. And then on the other hand, there are things where computers are better at proving things than humans, right? So there are decidable theories where if I toss the problem to a computer, it just more or less instantly knows the solution, whereas a human might have to stare at it for a longer time. And this actually happened, for example, with some formalization in Tarskian geometry that I did. So as a human, you have to like draw these diagrams and like carefully track, okay, so this segment is the same as this segment, right? And I state the same problem to the ATP, and it just like instantly knows the solution by some like heuristic exploration of the search space, right? This is like a very simple formalism of just like two basic predicates, and just like instantly explores the space and finds a solution, whereas I have to toil away and like draw things and use my geometric reasoning to sort of approximate this proof. But the fact that the ATP doesn't work the same way that my brain does is not really an issue as long as it's good enough, right? As long as it can find the proof, I'm happy. But there's of course some kind of long tail of things that are hard for the ATP to find. So this is an issue. We can sort of mitigate this by just using a variety of approaches. So there's different proof calculi. So superposition is the top one at the moment. But you can use other solvers. You can use SMT solvers maybe. And you can use specialized solvers in certain situations. And if you kind of expand this portfolio of automated theorem proving, you can get slightly better coverage. And then sort of in more detail for how the proofs work. So apologies for heavy notation, but sort of the main idea here is, with the first step, for example, this would be something where I just instantly end the proof. And this would be something that happens if I don't write a proof at all, for example. In this case, we have some kind of global context. So these are all the theorems and definitions that came before. And with the local context, so these are assumptions in the theorem, for example. And to prove it, well, we leave the local context intact because we kind of assume that if you write an assumption for the theorem, it better be relevant for proving the theorem. But on the global premises, we might do some kind of selection. So there are various approaches here, but so either you do this manually or you use some kind of machine learning, for example, to select which things might be relevant. And then you hand this over to the ATP. And if the ATP can prove it, then you're happy. And then the other steps here are kind of variations on this. So the second step is I give an explicit justification. I only need to explicitly cite the global things, because again, like the local things are assumed to be relevant, so I just leave them in. And then by assumption is kind of the degenerate case of that, where I don't use any global things at all. And there's other like terminals, like just using set extension directly. And then for the proof vernacular, so if I'm actually writing a proof, like a proper proof, I use steps like this. So the first two are, so the first one is just intermediate claims. So I just make an intermediate claim. I say, well, first of all, we know that this is true. And of course, this just means that within this context, I have to prove that the thing that I'm claiming is true. And once I've done that, I can proceed knowing that this is true, and it gets added to the local context. And again, the local context, so if I make some intermediate claim in the proof, that intermediate claim better be relevant for the rest of the proof. And of course, there's also ways of like reasoning against the goal. So you can make assumptions, you can reason against universal goals and all this kind of stuff. So this is like the typical proof vernacular that you would find in Mizar or in Isabel's Izar, this kind of style of proof vernacular. So the interaction with the ATP is quite tricky. So the problem is, for example, with superposition, that the way they prove things and the proofs they produce do not really correspond in the general case to how a human would prove things. So it is hard to present those proofs in a readable way. So, I mean, of course, you can just accept the automated theorem prover as a black box, but especially if I just write the theorem and I get an instant yes from the ATP, I might be interested in what the proof was, right? So this is a hard problem. One way of doing it is to kind of run the good prover first. So you run vampire first and get some kind of superposition proof. And then you look at the things that were assumed in this proof or the things that were used in the proof. And then you run another prover that is maybe a bit weaker, but is closer to how a human would prove things. So you might run like a tableau prover on the assumptions that were relevant in the vampire proof, something like this. The other problem is, of course, since we have this translation from controlled natural language to formal logic, this translation better not be surprising. So the important thing is, like as soon as you find something that is potentially confusing or ambiguous, it's better to just give an error rather than choosing some arbitrary disambiguation rule. So there's, of course, some kind of trade-off. Like, of course, we use like regular precedence rules, right? Like that is kind of a useful convention, but you have to be careful with this. Like, of course, you can try to like make up arbitrary precedence rules to disambiguate everything as you would like, but yeah, you might get issues with users writing things and they mean different things, and then the behavior of the system doesn't correspond to what the users might expect. And now it's time to reveal the evil plans. So this is joint work with Mario, who did a re-implementation of Mizar in Rust recently, with Atle Hahn, who's working on automated theorem proving, Peter Köpke, who is my advisor in Bonn, who worked on Approche, and Josef Uban, who is now my boss in Prague, who also worked on automated theorem proving a bunch, and especially also in the Mizar context. And the first evil plan is informalization. So the idea is the following. So I've dug out like 3 examples. So at the top, for each of these sections, you have some Mizar code. And below, you have sort of the equivalent controlled natural language thing that you might like. And our goal is to translate the Mizar thing into the natural language equivalent. And this translation should be, well, I would call it verification preserving. So I want this to be reversible. So I can parse back this natural language into a formal presentation that Mizar can understand and can still verify. So I can just switch between these presentations as I like. So why are we interested in, or why am I interested in Mizar? It's on the brink of being forgotten, which is very sad. So this is like the message, hey, Mizar exists, that's interesting. So the first thing is it's quite big. So of course this is all relative. I mean, MathLib, Lean's MathLib is bigger. Of course, I think now Rock and Isabel's proof libraries are also probably bigger. But in comparison to the Naproche libraries, Mizar is quite big. So this is a nice data set. Then the other thing that is nice about Mizar is we already know that ATPs perform quite well on this data set. So this is sort of not in an interactive setting, but sort of like as in, this is some kind of accumulation result over multiple years of using various approaches, various portfolios of automated theorem provers. But we're now at over 80% being of top-level Mizar statements. So this is just taking a statement in the Mizar library, a theorem in the Mizar library, and tossing it over to the ATP, and the ATP can solve this. I think this was like last year's result using CVC5. I think was the sort of the last thing that got it over 80%. So this was a nice result. But so this is kind of like a safe bet. Like I'm a coward. I want something that I know the ATPs already do well on. The other thing that is nice from like thinking about this weird tesseract thing that I showed earlier, right? In terms of natural foundations, well, many mathematicians don't care about foundations at all. But if they care, they might like wave their hands and say, well, ZF, set theory. And Misar uses Tarski-Grothendieck, which is basically ZF with like a slight strengthening. So this is kind of a natural foundation for mathematics, or it might be something that some mathematicians might consider natural. And the other thing that is useful, of course, is that the Misar folks are interested in this kind of presenting things in a natural way. And they have this journal, Formalized Mathematics, where they publish all Misar articles that are part of the MML. And as part of this publishing process, they have some kind of transformation tool that takes the Misar articles and transforms them into LaTeX documents. And that has a vocabulary mapping. So you take the Misar identifiers and you get some LaTeX pattern out of that. So why can we not just use this translation directly? Well, it's very lossy. For example, most of the proofs just get deleted. So this is of course an issue if you want to have a verification preserving translation. You better do something with the proofs as well. But this is a good starting point for getting some kind of vocabulary mapping. And then of course there's Misar-ORS, as I mentioned. So Mario did I think now 2 years ago, did a complete re-implementation of Misar in Rust, so you now no longer have to deal with some Polish Pascal code that is many decades old. So this is something that is maybe a bit easier to modify an interface with. So this is the evil scheme that now emerges. So since Anne Ranta isn't here and cannot hold his talk about Informath, I have to do the quote. So this is the don't guess if you know. So for this informalization thing, well, we know many things, right? We know the syntax and semantics of Misar. We know the vocabulary mapping that is used for this transformation for the journal Formalized Mathematics. So we better use this knowledge. So this is the kind of the motto behind all of this. So the plan is, well, we grab this vocabulary mapping, then we implement this verifiability preserving translation, so it's bidirectional, so we can reverse it and get back into some kind of Misar AST. And for that, I'm basically taking the grammar front end that I did for my naprosh.dev proof assistant and just like sort of bending it until it looks like Misar. And then once we have some kind of initial translation, we want to improve this translation, make it a bit more natural. So there's various things you can do. So I mean, a good inspiration for this is the Informath project that Anne Ranta is doing at the moment. So there's many kind of things you can just implement in the translation directly, like syntactic transformations that give you something that looks a bit more natural. But of course, you can try other things. You can throw an LLM at it, because that's what you do nowadays. You can just manually fix things, all sorts of things, right? You can do some kind of heuristics. And then there's other things that need to be improved. So for example, the theorems in Misar tend to have awful names like theorem 1, 2, 3 instead of useful names that a mathematician might prefer. So this, for example, is something that an LLM is quite good at. So you just throw the Misar theorem at the LLM and it will give it a reasonable name usually. Maybe a bit on the long side sometimes, but yeah, this works quite well. And then the goal is to have something that is readable as is to a mathematician without any special knowledge about Misar. That would be a nice result. And this is the vocabulary mapping that we have. So the Misar folks were kind enough to hand this into our evil paws. And so we had to do a bit of massaging. So one of the issues was that since it's sort of a write-only LaTeX patterns in this mapping, so this was not intended to be, like the LaTeX documents were not intended to be edited by hand. So these patterns included like detailed kerning information and things you would never want to write by hand. And of course, the way to solve this is to just wrap the commands into macros. So you just, through an LLM edit, come up with some macro names, define the macros for us, and then you get this mapping. And yeah, on the left side, you have Misar identifiers. So they have kind of funky terminology, but it has like obvious natural language equivalents. So like a functor, for example, might just correspond to some mixed fixed notation pattern. Modes in Misar, so these are kind of like types, would typically correspond to a noun, like homomorphism, for example. And attributes would typically just be adjectives. And you can see a lot of the mapping will, like a language is just a language, but instead of having this kind of like quasi-natural syntax that Mizar uses with the fixed keyword off and then just a comma list, we can do things like over, and, from, to, and so on to make it a bit more natural. But this was basically already like this in the vocabulary mapping, so we didn't need to do much here. And then the second part, of course, is once we have this informalization, it will be structurally faithful to the original Mizar article. And Mizar uses like a declarative proof approach, and they have this notion of obvious inference. And from a modern perspective, this is sort of like a very weak automated theorem prover. So the obvious idea is, well, we just replace the weak automated theorem prover by a strong automated theorem prover, and we can write shorter proofs. And there was already, like Josef already did like a sledgehammer style integration for Mizar, but this is of course something we would like to integrate into Mario's version of Rusty Mizar, to have sort of a proper interactive way of using automated theorem provers within the Mizar context. And once we have that, we can shorten the proofs. So we can start by very simple things, by just deleting subproofs, for example, just to delete random things and see if the automated theorem prover can reconstruct it. But of course, if you have something of the size of the MML, you would probably like to have some kind of more systematic approach, and especially a systematic way of evaluating whether or not your proof compression is good. Like if you're just deleting things that would be helpful to a human reader, that's maybe not a good thing to do. We really want to delete like tedious detail that are like uninteresting to a human reader. So this is going to be an interesting challenge, let's put it that way. And then the other challenge, of course, is once we introduce automated theorem proving, we quickly run into performance problems. So currently, things are nice. So this Rusty Mizar performs really well. Basically, so we did a run on some server in Prague. Of course, it's maybe a bit beefier than like your typical laptop, but this is still like not too crazy. And the library finishes basically in under a minute. There are like only 2 or 3 articles that are like using specific quirky features of Mizar, or like have some kind of quirky structure that take a bit longer. But basically, the entire library checks within a minute. And well, now here I come ready to ruin it. So by doing a more complicated parsing approach with using a controlled language, right? This adds a bit of overhead, but much worse is the automated theorem proving. So even if like the ATP calls would take like maybe a second on average, the checking time would still like balloon to multiple hours. I think like probably a day at least to check the entire MML, even if we got the ATP time to like 1 second, which is on the low side for an ATP. So there's some issues here. So we have to be smart about using automated theorem provers. Like if maybe there are some ways we can avoid using them in certain situations. And once we have a result, especially if it takes like multiple seconds to get the result, we better remember that we had this result. So caching becomes important. And then finally, we get to the thing I promised in the title of the talk, so autoformalization. So for a bit of context, I kind of want to dig out auto-coding. So this is maybe a way to refer to automatically generating code with a language model. So this is kind of like the vibe coding, as you would call it nowadays. But historically, autocoding was this. So this is from the 50s. So an autocoder was what now you would call a compiler. So instead of having, so the first thing is the binary, right? And as a help for the user, instead of having to write the binary directly, you would helpfully be able to write with some 32-bit notation. So the second thing is what you would write. This is very helpful for the programmer. I'm happy that I don't have to do this. And then sort of the autocode is so this is some random example, is the last line. So this is a bit like assembly code, right? So nowadays we wouldn't even call this a compiler, we would just call this an assembler, right? But this is of course much better than having to write the binary directly. And nowadays programmers just take compilers for granted, right? And I think in the same way, when we look at autoformalization, there's some things that you might consider autoformalizations that already happen and we already take for granted. And maybe in the future, there are things that now seem like science fiction that we also will take for granted, and we will not call them autoformalization, we would just call it formalization. So this is just to continue the analogy, right? So for programming languages, the results obviously vary quite a bit on what you do. So I can speak from experience. LLMs are pretty bad at Haskell, so there's just probably not enough data, or things are maybe too complicated or something. But if you ask it to write a bash script for you on some simple problem, you will probably get something sensible. But you need a lot of data. And sort of continuing this compiler analogy, I'm also not going to have good results if I ask the LLM to directly generate like bytecode for a VM or generate directly machine code. Of course, we get better results if we target a higher language, higher level language, and then leave the rest to the compiler, right? So we want to do maybe the same thing with formal things, and then sort of extending this don't guess if you know, maybe don't guess if you can calculate, right? So if you can leave certain things to something that we know works, so in this case a compiler, we get better results. So on the formal side, well, obviously it's going to depend on the proof assistant, but the main issue here is that, of course, there's much less formal math than there is code, right? So I briefly looked into this. So, I mean, I think now the sort of largest library is Mathlib. I think they like recently hit 2 million lines or something in August, if I'm not completely wrong. If any lean people know better numbers, let me know. And I mean, there are single Python projects that have like 20 million lines of code. So they're like individual Python projects have an order of magnitude more. And if you look at all the Python code that is somehow like floating around on the internet, it's probably like multiple orders of magnitude more than there's lean code. So there's some kind of data problem there maybe. And then again, like if we have to leave certain things to the compiler, maybe we should leave certain things to more deterministic or more specialized solvers. So, I mean, for proof assistance based on type theory, of course, you would also include type checking here, right? You don't want the LLM to do the type checking for you. You better reuse the type checker of Rock or Lean for this. So this is kind of an obvious thing, but maybe it's good to extend this to more automation, right? This is kind of the propaganda for automated theorem proving that I wanted to pitch. And again, don't guess if you can calculate, right? If you have a special solver that can do this, if you have a problem in ring theory and you have a ring solver, you should probably ask the ring solver and not the LLM. So what are we doing? So we just started this project, basically. But the idea or the intuition behind it is, well, if we want to do autoformalization to controlled language, maybe we can kind of benefit from all these quasi-formalists that I had on the very first slide, right? These people that kind of try to pretend to write formal mathematics. Maybe there's enough of that floating around on the internet that the LLM can sort of pull off a kind of quasi-formal thing, and then we can make the leap to controlled language. So that is maybe it's wishful thinking, maybe there's something behind that. But what we have observed is that just by simple prompting, we can get LLMs to kind of respect the grammar of a controlled language. So this works surprisingly well. And on the other hand, if you get something that doesn't fit the grammar, maybe that's a good pointer to extend your grammar, right? And if you really wanted to, you can use grammar augmentation. So you can use syntactically constrained sampling to really force the language model on a low level to like be constrained by a certain grammar. So this is, for example, something you can do. I think OpenAI has like an API where you can like force JSON output to be valid, and this is what they use. And then another thing where like this informalization project with Mizar might come in is, well, we already know that this works, right? Like the Mizar proofs can be checked by Mizar, so this is kind of like some kind of high quality, semi-informal looking thing that we can maybe use as a source for how proofs should look. But of course, there's all these inherent difficulties in autoformalization. So especially if I want to do some larger project, I might have like dozens of definitions, and if I get one of them wrong in a subtle way, the whole thing might come crashing down, right? So there's many difficulties there, and of course there's also just things that mathematicians leave implicit. So I mean, my example is always the Stacks project, which is this like 7,000 page collection of stuff on algebraic stacks and this kind of stuff, algebraic geometry. And there's lots of things that are implicit. Like if you look at the diagrams that they use, many things are not labeled. There's some kind of canonical map that a mathematician understands. This is the thing you use here, but there's nothing explicit in text that refers to that. Lots of, and of course, like this reasoning that I mentioned, like reasoning by analogy, reasoning by geometric intuition, are also still hard to model. But what we do is, we currently, so this is we pick an easy target. So this is working on inverse semigroups. But so the first step is to get things in a pre-processed way to make them a bit more manageable. So we take the original source. In this example, the source that we're using, the definitions are not necessarily like in individual environments. They're sort of more in the running text. So we extract those and put them into individual environments. And then we give nice labels to the environments, and we highlight which is the term that is being defined. And we also try to like grab all the background knowledge that is assumed in the textbook. So this is like a typical thing for a mathematical textbook. Like they might not explain or define what the union of two sets is, right? They might just assume it and use it. So there's some kind of well-known concepts that are assumed for these definitions. And then the second step is to use those pre-processed definitions that are sort of split and prepared to use a reasoning model to actually get them into controlled language. And currently there's just a large prompt that basically explains the grammar to the language model. So this is not the full grammar just like copy pasted into the language model. It's sort of like more just this is an example for how things should look. If you write it this way, this doesn't work. This kind of stuff. And then there's a simple feedback loop. So if the system says, you messed up with your syntax, and gets an error message, and then it tries again with that error message in the new prompt. So these are like the very early, very initial results. So this is, I think, like as of yesterday, got updates from Atlas. So we went up from 80. So we just started this basically. So we already went up from 82% to 97%, at least being syntactically correct. So there's still maybe some semantic errors, but at least we get like valid controlled language. And the time to generate this went down from 10 hours to 2.5 hours. So this is like a fairly promising start, I would say. And the main idea is to kind of use the controlled language to separate the incidental difficulties of autoformalization to like the real difficulties, and seeing how far we can get. And this is one example I picked out. So the top is the kind of the pre-processed definition. So this is extracted from the running text. And you can see it gets packaged already in an individual environment. We already have a nice label that we can reuse. And we have this highlighting of the term that is being defined by using this \emph. And then below we have the formal. Here the emph goes away, right? This is just like the thing that is being defined is kind of clear by the controlled language. We reuse the environment, we reuse the label, and then we just rephrase the definition in a more explicit, more controlled way. And the last thing I want to point out here is that this is like just using the basic features of the system. So for example, we're not using, there's some built-in mechanism for structures. We're not even using that at the moment. So this is like a very simple, very low-level approach with just tuples to encode the structures. But it sort of works. Yeah, and of course, this could be like made a bit prettier by using like a more sophisticated approach to the notation instead of like this M and S, M and I for the operations of the semigroup. But yeah, that's for the future. Again, we just started with this. But yeah, this is sort of our hope, that we can just continue doing things like this and seeing where we end up. And that's it for now. Thanks.
Okay, are there questions? Oh, okay.
Yeah, thanks.
Thank you very much. Very interesting. I just want to.
Thank you.
And probably relevant piece of history, even probably it's prehistory.
Yeah, I'm glad to hear it.
It's actually Giuseppe Peano, who, I know everyone knows for Peano axioms, which he indeed made more or less in modern form. And actually, he dealt with this problem, with formalization.
Yeah, there's Latin without inflection and so on, yeah.
Symbolic language, and he used something like controlled language,
yeah.
which he called interlingua, which is version
no, I think
like
it's Latin without inflection. Yeah.
But that's exactly, he dealt with this problem. So you have formulas and you want, okay, but that's, then actually, my question is this. Yeah. Then you mentioned Glushkov, the Soviet.
Yes.
Yeah. And actually, no, at least it's my observation, maybe. The Soviet program, Glushkov, was very much focused on proof search, not while, say, contemporary automat was no search capacity, right?
Yeah, so there's two versions of SAT.
And today, then earlier it looked like a failed strategy, but now it looks like probably good strategy. But the question is that now this business of formalization, deformalization, as you described, if I understand correctly, concerns, presentation of proof, right? You say how to present to human automatically generated proof. So my question is there, I don't know, room for something similar in, say, proof search? And you can kind of imagine it, right, that when you interact with human during search and not for, yeah, is there some, I don't know, work and what you think?
So not directly in this project. I mean, the thing that might be most relevant here is Enigma. So there's these, there's like these state-of-the-art automated theorem provers like E and Vampire. And for E, for example, so they use like some kind of internal way of keeping track of the terms that are being used and so on. And this is something that Josef can say in more detail than I can, but there was like internal guidance with machine learning in E, for example. This was this Enigma project. So an avenue like that might be quite interesting, where you combine like an automated theorem prover with a calculus that is known to work well, like superposition, and you combine that with machine learning to kind of do something that maybe more models the way that a human might explore a search space. But yeah, indeed, like the SAT project that I mentioned in this historic overview. So this first phase of this EA stuff, there was a Russian version of SAT, but this was only the statements of the theorems. So you would write the statements in a Russian-controlled language, but the proof would be fully automatic. This was the dream, right? So, and then the difference with this English SAT that Paskevich did was that he extended, well, he made it in English, right? That's the first thing. And then he added a proof language that was kind of inspired by Mizar, I guess, where you can write the proofs and then the ATP only has to go step by step instead of having to do the entire thing.
But otherwise it was close to Mizar, actually, at least in mature form.
Yeah, the spirit is very similar, yeah. I mean, there's a lot of things that are sort of in the background in this EA thing, right? They had their own calculi, and they have this notion of evidences. So this is something that is actually implemented in Paskevich's SAT. I'm not an expert on this, but there is the idea of you kind of go through the text, and besides the sort of explicit things that a user might write as intermediate information, you accumulate evidences and you also keep track of that. But actually with modern ATPs, this doesn't help you. So there's a feature you can turn off and on in SAT, and you get better performance when you turn it off. So, and there's other things in SAT where you get better performance when you just turn it off. Yeah.
Okay, so maybe Jim, you want to ask?
So you already told us a little bit about the prompt that you're using to make sure that it outputs valid controlled natural language. Can you say a bit more? I think this is very interesting.
Yeah. Okay, so the prompt basically, so it's a fairly long prompt. I think there are some examples in there, and it kind of like frames a way of doing things for the LLM. So it says like, a definition uses the following approach. There's like these types of definitions. There's like a definition of a noun, for example. There's a definition of an adjective. And to define things, you follow the schema. And it sort of like breaks down the way you can define things in smaller like smaller different steps. And then based on that, kind of the LLM is supposed to branch off into whichever definition it's supposed to take. Yeah.
And can you give an impression on how long is long?
I think it was like multiple kilobytes. It was like 8 kilobytes. Two. Yeah.
2 to 3 pages. Okay, thanks.
But of course, you can do different approaches there as well. Like you could try to like fine tune an LLM, or you could like again, like the syntactically constrained sampling might be interesting in the long run. Yeah.
Okay, Henri?
Yeah, thanks. You mentioned Informath several
Yes.
times. I'm going to give a talk 3 p.m. Not strictly about Informath, but just grammatical framework.
Yes. Yeah.
So would you see this as like a parallel effort to Informath, or kind of?
Yeah, so I was very glad to be able to talk with Anne multiple times. Like I met him in Prague, and we met in Prague, we met in Ossois, and recently in Orsay. So I got a lot of chances to talk to him. And I mean, I should probably credit like part of this grammatical thing. Where is it? So this was the reason why this exists. Is well, in 2020. I was sitting there doing like the parser combinator thing, and Arne took me by the side and said, "Well, you shouldn't do this," and that probably saved me quite a bit of stress. So I'm very thankful for Arne to telling me to not do some other approach. And yeah, indeed. So I mean, there are some. So the Haskell code that Informath uses, right, like the way of rephrasing or choosing certain formulations. I think that is something that I can maybe almost at least structurally reuse one-to-one for this Mizar informalization. So I think that would be very useful. And then the other thing is like using GF. So the kind of architecture I came up with is like pre-processing of like grabbing all the vocabulary to kind of like parameterize the grammar with. That is something I came up with in trying to think about how can I model this dynamic aspect with GF, right? Because at the time, GF was like a static compilation thing.
Oh yeah. I mean,
So
this is
this
not
is-
a criticism. It's just I'm very curious because I know better than anyone here that GF has definitely its shortcomings. So I'm just like.
So I mean, Anne told me that there was some work on like grammar as a database, which would of course be very interesting in this application. And I'm also very interested in GF just for performance reasons. So with the scale of Mizar, like with the number of vocabulary items, you do get into a situation where the current library I'm using actually hits performance issues. So I have to like cut down the vocabulary to things that are only used in the current text. And GF probably does it better there as well.
I have more questions, but I'll take them
Yeah.
offline. So I guess like I think I'll let.
Yeah, we should probably talk later about GF. I also have a bunch of questions about GF. Yeah.
Okay, so I think we should really thank Adrian. Yeah.
Thanks.